Okay, so the goal of this video is to look at a few more practice examples, and just kind of again get a little bit, used to using, the nth term test, or trying to show something converges, diverges, and is it a series that we're showing, or is it a sequence of terms that we're showing? So I thought I'd start with example D, and so this is sort of I guess I don't want to say like maybe it's a familiar, maybe it's a familiar limit problem. We just had it on our chapter 7 test. So if you imagine just for a second, if you just had like the equation, let's say like y equals 1 plus 6 over n to the n. So we want to show like, hey, maybe these terms aren't going to 0 because they're not, right? So these terms are not going to 0. So I want to use the nth term test, but I want to show exactly what is the limit. So I, like on the AP exam, you can't just say, oh, the limit as n goes to infinity is not 0, therefore it diverges. You have to actually be able to show that. So this right here, if you remember, we can log both sides, bring that n down. So this comes 1 plus 6 over n. Oh, sorry. Natural log. How unnatural of me. Sorry about that. So natural log of y equals n, and then it's natural log of 1 plus 6 over n. And let's just focus on the right side for a second. Let's make that n is like 1 over n. And now we are sitting in a case where we can use L'Hopital's rule. Because as n goes to infinity, the top becomes natural log of 1, which is 0, and the bottom also becomes 0. So as I take the limit, as n goes to infinity, since I'm in 0 over 0 indeterminate form, I can use the L'Hopital's rule and say, okay, so that's the limit as n goes to infinity. So the derivative of the top, it's 1 divided by 1 plus 6 over n. And then chain rule, the derivative of 6 over n becomes negative 6 over n squared. And then the derivative of 1 over n is negative 1 over n squared. Now, let's go ahead and sort of like simplify some things. Well, the n squareds will cancel, and negative 6 divided by negative 1 is a positive 6. So we get the limit as n goes to infinity of 6 over 1 plus 6 over n. Now, as n goes to infinity, this term here goes to 0, so I can actually show that this equals 6. But remember, this is natural log of y equals 6. So if the natural log of y is equal to 6, that tells me that y is equal to e to the 6th. So now I can, I've justified, I can show that this series converges by the nth term test. So I can say series... if I said converge, I didn't mean to. Diverge. For some reason, I was just thinking ahead. I just thought I said the word converge. The series diverges by the nth term test. And again, remember, the series is the summation of this, right? So the series diverges by the nth term test because the limit as n goes to infinity of the term 1 plus 6 over n, to the n. I should probably put that in parentheses. I'm just realizing that now. So as n goes infinity of the terms 1 plus 6 over n to the n equals e to the 6th, which is not 0. So that's kind of like the justification. You have to show me what the limit is, and if it's not 0, then the series itself diverges by the nth term test. And again, because the terms aren't getting smaller. If the terms aren't getting smaller, there's no hope for them to actually converge as a summation. Okay, so I like that one. Okay, so I guess I gave myself a lot more work space than I thought I needed. That's okay. So the next one, part E, I want to show that this series does converge, And right now, we don't have any tests to use other than using the nth term test to show that the series fails, right? Or is it something that we recognize? Is it a geometric series that we can actually find the sum? And in this case, it's not geometric, but it is a telescoping series. And if you can actually find the sum, then you know that the series itself converges because you can actually find it. And I know it sounds strange, but like most of the times, we're not going to be able to figure out what the sum is. We're just going to be able to show, oh yeah, it converges to some value, but we don't know what it is. So let's review rewriting this. The bottom factors into x plus 12, x minus 1. Right? So we have a over, or in this case, n plus 12 plus b over n minus 1. Since that factors, so I'm going to go ahead and try to figure out what those a's and b's are. So 13 equals a times n minus 1 plus b times n plus 12. And choosing, smart values of n, if you remember this from partial fractions. So let's let n equal 1. That tells me that 13 is equal to 13 plus 12, 1 plus 12, which is 13. So 13b, it kind of works out nice. B is 1. And then if n is negative 12, look at that's nice as well. 13 is equal to negative 13a, which means a is negative 1. So, I mean, it is nice that these are opposites of each other. They don't necessarily have to be, but it is nice that they are. And that's 1 over n minus 1. So now my summation here, what that, I guess what I can analyze is the sum of these two individual series or sequences, or partial fractions, sorry. So if we take the summation n equals 2, good thing we're starting at 2, right? To infinity of negative 1 over n plus 12 plus 1 over n minus 1. So if you look at when n is 2, so the first term of the negative 1 sequence will be negative 1 over 14, and then there'll be a negative 1 over 15, and that goes on forever. The first term of this one, when n is 2, is 1 over 1. So get 1 over 1, which is 1, plus 1 over 2, plus 1 over 3, plus 1 over 4. And this is going to keep going until forever, but notice where it becomes sort of significant. 1 over 13 plus 1 over 14. Wow. Like right there, that 1 over 14 is going to cancel, the tail end of that's going to cancel with everything there. And so that's quite a few terms to cancel. So it ends up, it is finite. It's just, 1 plus 1/2 plus 1/3 plus 1/4 up to 1/13. So I can say that the series converges since I know what the summation is. So the series converges, and I know exactly what it converges to. So if you can actually state what that sum is, that's sort of your test. Like you're like, oh, I know it converges, and here it is. And so if you want to write that cleanly, you could say it converges to n equals 1 to 14. It's the first 14 terms of just 1 over n minus 1. I mean, that's a real clean way to write it, right? It's finite, and it's 14 terms, because notice that this represents the 14th term, 14 minus 1, which is 13. So we definitely know it converges. And notice there's no test. We haven't written, nth term or no, I guess you could say converges because it's a telescoping sequence, and we know exactly what the sum is. Okay, so then our last one, this one is one of my personal favorites. If you had me for HPC, you know that I like to call this the best of both worlds, or the Miley-Cyrus sequence, because the numerator is increasing by 1. So the numerator is arithmetic. The denominator is geometric. So when you have something that's like arithmetic divided by geometric, so the terms are changing, but they are getting smaller, and we can show that they're getting smaller fast enough that we can actually find this sum. So the way to do this, if you remember, is I just called what we're looking for S for a sum. I'm just rewriting this here. And then whatever the geometric part is. So I'm noticing the geometric part is up by like 3, right? Multiplying by 3. So whatever the geometric part is, you're going to multiply both sides of your equation by that geometric part. So I'm going to say 1/3 the sum is equal to, so then it'd be like 2/3 plus 3/9 plus 4/27 plus 5/81. Okay, so again, that's just the geometric part. And then you subtract. So when I subtract, so S minus 1/3 S. We'll think of there's like a 1 sitting in front of there. So 1 minus 1/3 is 2/3. And then we want to subtract in a fashion that the denominator's already been, solved for us, so to speak. So like right here, like 3 minus 2, like 3/3 minus 2/3, that's 1/3. There's 1/9. There's 1/27. There's 1/81. So we have this kind of orphan term, 2, plus, and then then we get 1/3 plus a 9th plus a 27th. In other words, we found a finite amount in front, aka the 2, and then an infinite amount that this is geometric. So that geometric component, I'm going to just add up using a over 1 minus r, a being 1/3, because I'm just starting there. 1 minus, it just happens to be that the starting term and the common ratio are the same. So we get 1/3 over 2/3. And then that adds up to 1/2. So the tail end, basically everything but the 2, right? So all of this adds up to 1/2. So now look at our equation. Oops, there it is. So now look at our equation. So we know that 2/3 the sum is equal to 2, because we had that 2, plus all of this, which is equal to 1/2. So 2/3 the sum is equal to 2.5 or 5/2. So just multiply by the reciprocal. 5/2 times 3/2, which is 15/4. So we can say that the series converges. Series converges. Remember, series means sum. And how do I know it converges? Because I can actually calculate the sum. So the series converges to the value 15/4. So again, anytime that you can actually show what your series equals, you can sorry, it's caught on the cord there. Then you know exactly. You could state it converges because I can show you exactly what the sum is. So okay. So I just liked going through those 3 examples, just because I think it's good to see and hear and watch. Especially with this chapter being so different than pretty much what you've seen all year long. So okay, excellent.